What is 2.5 factorial? 2.5 factorial equals what? Factorial is usually a discrete machine, 1 factorial, 2 factorial, 3 factorial, just dots at integers. But here's the promise. If we can make factorial a smooth curve, we can take its derivative. First, a quick warm-up. For a smooth function like x squared, the derivative is the slope of the tangent line. Slide the tangent. Right there at x equals 1, the slope is 2. Now switch to x factorial. Look, only isolated points, 0 factorial, 1 factorial, 2 factorial, 3 factorial. Try the limit definition with a tiny h, and everything breaks. No nearby values, no consistent tangent, so the derivative is undefined. The fix is the gamma function, f of x equals gamma of x plus 1. Same factorial values at the integers, but now it's continuous in between. And now the tangent exists. At x equals 2, the slope is about 1.845, so factorial has a derivative anywhere. Let us explore it. Let us explore the definition that makes x factorial work for every x. For integers, factorial is a product. N factorial equals n times n minus 1 times 1. But Euler's idea is stop multiplying and start integrating. Define x factorial equals gamma of x plus 1, and gamma of z equals the integral from 0 to infinity of t to the z minus 1 times e to the minus t dt. That's the key. This integral doesn't need where do we stop. It automatically produces a finite number for non-integers. From the previous section, factorial was trapped on the integers. Now we break out. The gamma function makes factorial continuous. Think of gamma of z as a smooth curve that doesn't jump from 2 factorial to 3 factorial. It connects them. As z slides, the value changes smoothly and the point glides along the graph. At z equals 3, it matches exactly 2 factorial. At z equals 4, it matches exactly 3 factorial. But the real messages between them, z equals 3.5, is not undefined. Gamma fills in every in-between value, so factorial becomes a continuous function, not just a list of integer answers. Now we go deeper. If factorial is continuous, we can talk about its slope, its derivative. Start with the definition. Gamma of z equals the integral from 0 to infinity of t to the power z minus 1 times e to the minus t dt. Differentiate with respect to z. Only one piece depends on z, t to the z minus 1. Here's the key identity. The derivative with respect to z of t to the z minus 1 equals t to the z minus 1 times the natural log of t. So the derivative becomes gamma prime of z equals the integral from 0 to infinity of t to the z minus 1 times the natural log of t times e to the minus t dt. That's the exact slope, but it's not easy to simplify. So we introduce a helper function that measures relative growth, the Digamma function. Define it like this. Psi of z equals gamma prime of z divided by gamma of z. This is the same as the derivative of the natural log of gamma of z, because d over dz of the natural log of gamma of z equals gamma prime of z over gamma of z. Now we can rewrite the slope in a clean product form. Gamma prime of z equals gamma of z times psi of z. Next, we find a simple rule for psi of z. Use the gamma recurrence. Gamma of z plus 1 equals z times gamma of z. Take the natural log of both sides. The natural log of gamma of z plus 1 equals the natural log of z plus the natural log of gamma of z. Now differentiate both sides with respect to z. The left side becomes psi of z plus 1. The right side becomes 1 over z plus psi of z. So we get the key recurrence. Psi of z plus 1 equals psi of z plus 1 over z. Now apply that step by step for integers. Start at z equals 1, psi of 2 equals psi of 1 plus 1, psi of 3 equals psi of 2 plus 1 over 2, which is psi of 1 plus 1 plus 1 over 2. Psi of 4 equals psi of 3 plus 1 over 3, which is psi of 1 plus 1 plus 1 over 2 plus 1 over 3. See what's happening? Each step adds 1 over n. That growing sum has a name, the harmonic number. So psi of n equals minus gamma plus h sub n minus 1. And that's the payoff. The derivative of x factorial equals x factorial times h sub x minus gamma. Now let's make this derivative feel real with a concrete example. We've got the formula, the derivative of x factorial equals x factorial times negative Euler's gamma plus h sub x. So plug in x equals 2. 2 factorial is 2, and h sub 2 is 1 plus 1 half. That's 1.5. Euler's gamma is about 0.577, so inside the parentheses we get negative 0.577 plus 1.5, which is about 0.923. Multiply by 2, and the slope at x equals 2 is about 1.846. Now, let's see that slope. On the graph, the curve is x factorial, really gamma of x plus 1, so it's smooth. A dot slides along the curve, and a tangent line rotates as the dot moves. Next to it, we display the slope value in real time. This is d over dx of x factorial. Watch as we return to x equals 2. The on-screen slope reads about 1.846, matching the calculation. And here's a surprise. If we slide left, the slope eventually hits 0. That happens around x equals 0.46163, where the curve reaches a minimum. So the final takeaway is simple. The derivative of x factorial equals x factorial times negative Euler's gamma plus h sub x. Thanks for watching.